Hey, good morning. Wonderful being here. So, to realize this new era in computing, we need hardware and we need software. I won't focus on the hardware, not because it's not important, it's very important, only because we are in good hands. We just heard Psi Quantum, after we'll hear Fujitsu, after we'll hear Kuera, and many other companies are making amazing progress. We'll focus on end users, on the people that actually need to program these machines. And that's actually also the focus of the Japanese government, targeting 10 million quantum users by 2030. Very ambitious, also very challenging because already today we face a great shortage of quantum talent, quantum workforce. When we envision will be the people to program quantum computers, who will be this workforce. So of course, there are the quantum experts, but we also need the domain experts and software developers, right? The problem is they can do very little. When we established this company 4 years ago, that was the state of the quantum software stack. Basically, it didn't exist, right? The development was limited to gate-level programming, and abstraction was yet to be built. And therefore, software engineers could do nothing, domain experts could do nothing, and the leading quantum experts could do something, right? Could develop small toy models, non-optimized quantum circuits. And for the past few years, we are focused on enabling quantum software at scale, building the most advanced quantum software stack that will fit all type of users. We have a team of 65 engineers located in Tel Aviv, also in Tokyo. And what we have been doing for the past 4 years is creating this end-to-end quantum software platform that is both hardware agnostic and most importantly, it allows quantum software at scale. What does it mean? It means abstraction, being able to develop quantum software in a very abstract way at the model level, not at the gate level. It means scalability to any number of qubits, not focusing on toy circuits for 10, 20 qubits, but scaling up to hundreds, thousands, and millions of qubits, automatically, of course, and performance, making sure that the circuits we compile are the best possible circuits, much more optimized than anything else that could be done manually. So we'll focus on each of these aspects, but before that, I want you to see how it looks like. So this is the Classiq platform. You enter, you have many pre-built applications, algorithms, models. And now we'll focus on the one that we see on the screen. So this is a very short code, very abstract code embedding classical logic within a quantum circuit. We compile it and we see that this circuit is already fairly complex with 35 qubits. You can open it, of course, you can explore it. But let's say you want the same logic to work only with 9 qubits. So you come back, you ask the compiler to try and meet this constraint. It succeeds. And the trade-off is a bit deeper circuit that meets your constraints. You didn't change the model, of course. The model remains the same. Then you can execute it. We choose IBM Kyoto machine. You can see how the qubits are allocated on the specific chip. And of course, you can send it for execution, by the way, on IBM, but on any quantum cloud, any universal quantum computer, and you get the results. So what we have seen here basically is an end-to-end quantum software flow from application libraries, development tools. In this case, that was the Classiq IDE. We also have a Python SDK, high-level language, which is the QMod language I'll elaborate on, compiler at scale, scalable true compiler, and of course the operating system of execution on actual hardware. Now let's dive into the different modules. So QMod is the first high-level quantum programming language in the sense that it allows you to describe a functional model that focuses on the functional intent, not on the implementation. Implementation is done by the compiler that takes into consideration the functional demands, the hardware constraints, and it synthesizes a gate-level circuit out of both of them. So QMod allows the abstraction, the ability to easily develop any complex quantum algorithm at scale. It's accessible in 3 different methods: in the native textual syntax, what you just saw on the IDE, in a graphical interface, like a Simulink style, right? And in a Python SDK. But the language is not very useful if you don't have an underlying strong compiler, which is exactly what we have built. And this compiler is a true compiler in the way that it doesn't get as input a concrete quantum circuit, it gets as input a model. And it has the flexibility, huge flexibility by the way, to choose the implementation. So for example, these 3 circuits you see here, very different between each other, all are doing the same, the very same functionality. So the compiler has huge flexibility out of billions of circuits to find the best one, or the one that best meets your constraints. Unlike, by the way, a transpiler that we are very used to, right? That has very little flexibility because it gets as input a concrete circuit. It's unaware of what you want to achieve. It's aware only of the circuit you give it, so it's very limited in the level of optimization it can achieve. So the compiler is what allows us to stay with the same model, to change the constraints, and to get very different circuits out of the same model. It also allows us the scalability. What you see here, this is a full implementation of the Shor's algorithm. We are very used to this algorithm. We are used to seeing it on paper. But my guess is that this is the first time you see an actual implementation, a scaled implementation, very complex, by the way. And this is enabled by these compilation and synthesis methodologies. What it also allows us, surprisingly, because it contradicts the abstraction, it allows us to achieve the state-of-the-art results. And why is that? Because when the compiler has this big flexibility from high level to low level design optimization, it can choose the most optimized results that meet your constraints. So for any quantum algorithm, anyone, we show dramatically better results than anything else on the market. Here you see HHL, Statorcal generation. Also, by the way, beautiful work by the Deloitte Japan amazing team, in this case on the QPE implementation. But basically for any quantum algorithm, you can just see dramatically better results, even for small circuits, definitely for large circuits, but even for small circuits. The Classiq engine, this compiler, is accessible both via the Classiq IDE and SDK, but also via other development environments, like NVIDIA CUDA Quantum, like a classical computational software such as Wolfram, and it streamlines the way to quantum hardware. And of course, most importantly, it allows all quantum users to develop quantum software. It fits all quantum users today and in the future, the domain experts, the quantum experts, of course, and the software engineers. But what's really interesting is not what we do with the platform, is what users, customers, partners, academic users, educators do with the platform. So I'll give some brief examples. Of course, there are many examples. The first one will be from the finance industry. So these are two nice examples from Citibank and Intesa Sanpaolo. And actually, what is very beautiful about these specific teams is these are teams built not with quantum experts, but with domain experts, software engineers, and they have been embedded into quantum programming with Classiq, showing very impressive results. Two different examples from different industries are Rolls-Royce and BMW that created some of the most complex quantum circuits I've ever seen. I think anyone has ever seen. The HHL algorithm and the unit commitment algorithm. As you can see in both cases, it was in deep collaboration with our partners and friends at NVIDIA. In HPC applications, we work closely with HPE to embed a Classiq engine as backend to the Cray programming environment. And of course, also very much focused on academic research and education with Microsoft, with Wolfram, and of course with many universities globally in order to create this next generation of quantum workforce. Japan has been a strategic market for us since day one for many reasons. You know, we found here industry experts and investors and partners and customers and many colleagues and friends. And we were very privileged last November to establish our local office led by Tanaka-san, who is an industry leader, and he leads our Japan activity, actively hiring. I think many of you have already met him, but you are all very much invited to our office. And definitely we look forward to growing Japan. This is the best place to build the future of computing. And also you are very much welcome to join a hands-on workshop on Classiq tomorrow in our office tomorrow morning. You are all welcome. And thank you very much. Would love to answer any questions.
Thank you, Mr. Minerbi. Just a reminder that you can submit your questions via Slido. You'll see the QR code right over there. So if you have any questions, I should have said you can submit your questions both in Japanese and in English. I'll do my best to interpret, translate on the spot. なので、日本語でも結構ですので。
So, of course, you can ask questions in Japanese. If you have questions, please use the Slido with this QR code to ask questions. Or we can take questions directly. We have a microphone. If you raise your hand, we can take your questions here.
We don't have any questions so far, but maybe just on the last point in terms of setting up the Japanese entity and continuing your engagement in Japan, perhaps you can speak to what your expectations are for the Japanese market moving forward and perhaps also the Asian landscape overall.
Sure, I think the Japanese market is very advanced, both in terms of end users, hardware providers, HPC providers, service providers that are building their own internal quantum capabilities. Japanese engineers are doing impressive work. They do with the platform things that we couldn't imagine possible. So this is both challenging and exciting. So I think, you know, this is a very natural place to expand into. It was a no-brainer.
Excellent. Well, we're excited to have you here. Thank you again very much.